Hello and welcome to PCMINR.com, and you're watching this video on total energy in simple harmonic motion by Sonal Gupta. Now, how can we find out the total energy in simple harmonic motion and show that it is constant or it obeys the law of conservation of energy? Now, first of all, a particle which is executing a simple harmonic motion possesses two types of energy, and they are the potential energy and the kinetic energy. Now, we have to prove that they both or the sum remains constant. So, first let's calculate the potential energy in simple harmonic motion. Now, if we assume that m is the mass of the particle we are talking about, let's just write down all the parameters first. So, we have m as the mass of the particle which is executing the simple harmonic motion. A is the amplitude, which will be like this, the maximum distance from the mean position, that is at the extreme position, and omega is the angular frequency. Then at any instant, we know it's a simple harmonic motion, therefore at any instant t, the displacement of the particle would be given as y is equal to a sine of omega t. Now, if y is equal to a sine of omega t, therefore the instantaneous velocity, as we know, is dy by dt. We can say this is v, and that would be the differential of sine omega t would give us cos omega t into omega. So, we get a omega cos omega t as the velocity. And further, if we can mark it number 1. And further, if we differentiate it, we get the instantaneous acceleration. Therefore, the acceleration at any instant t would be, a is equal to dv by dt, and now we differentiate that equation again, we get minus a omega square sine omega t, because differential of cos omega t is minus sine omega t into omega multiplied by a omega. So, that is our acceleration, right? And if we just compare it with the first equation, a sine omega t, we can write this is equal to minus omega square y. That is my acceleration. So, this is the important equations, or all the three are important. We would use them one by one. Now, we come to the calculation of the potential energy, because here when you stretch something, or in case of a simple pendulum, when it goes to this side, there is a restoring force acting in the string which pulls it back. Now, that restoring force is always proportional to this displacement y, and in the negative sign because it is directed opposite to the displacement. So, I would get F as equal to, we can just clear this whole thing, and we get F is equal to mass times acceleration, one is that, and we have to equate it with the minus ky thing. Now, mass times acceleration we calculated is just minus omega square y. So, I get minus omega square y, and that is equal to minus ky. Therefore, I can always use m omega square as to be equal to k. Hence, what is the potential energy? The work done against this restoring force will give me the potential energy of the simple harmonic motion. Now, therefore, if we say dw is the small amount of work done in displacing against the restoring force, so that would be f dy. So, that's negative of negative ky dy, that gives me plus ky dy, and so the total work done, therefore total work done for the complete displacement from the mean position to the extreme position would be, the total work done is equal to w is integral of ky dy when you go from the position 0 to the maximum displacement y. So, we get this as half ky square. Either we can use this equation, or we can use that potential energy is half ky square, or we can also write as half m omega square y square. If we write this as k m omega square, just plug in the value of k and we get this as the potential energy. Now, we can note down this. Now, we move to the kinetic energy part. Kinetic energy is quite simple to calculate because it's just half mv square. So, we have now the kinetic energy of the particle at any instant. So, kinetic energy at any instant t would be given as kinetic energy is equal to half mv square, and we have already calculated the expression for velocity. So at any instant, velocity is equal to a omega cos omega t. So just square this up and we get it as half m omega square into a square cos square omega t. We can write this, and also we can write it as half m omega square into a square. We can keep a square outside here. Cos square omega t is 1 minus sine square omega t. So we can write this as half m omega square a square into 1 minus y square upon a square, because y is a sine omega t, so sine omega t would be y by a, so this becomes y square by a square. So this is half m omega square a square into 1 minus into a square minus y square, and upon a square. This would cancel out, so I get the expression for kinetic energy as half m omega square into a square minus y square. So what is going to be the total energy of the particle? Now this is the expression we got for kinetic energy. We already calculated, this is the kinetic energy. The potential energy we calculated was half m omega square a square. So if we add the two, we would get, this was our equation 4. So the sum of these two would give us the total energy of the particle. So let's just add them and we get the total energy as E is equal to u plus k. So that would be half m omega square a square plus half m omega square a square. Sorry, this a square was cancelled out, into a square minus y square. And when we open up this bracket, we would get energy as half m. So this is half m omega square y square plus half m omega square a square minus y square. And when we add them, this positive and the term we'll get here will be negative. Half m omega square y square would cancel out. So your net energy turns out to be half m omega square a square. And we believe in simple harmonic motion, our m, omega, a, they are all constants, which obviously means that the total energy of the particle which is executing the simple harmonic motion would remain constant at all times, because it's not dependent on anything else. This is half m omega square a square, which is constant. We can also show that, like if this is the expression, what would you get the energy at instant t is equal to 0? So therefore, in the special case at t 0, your total energy would be equal to the potential plus kinetic, but potential energy is going to be 0. Why? Because at t0, this y would be 0, right? At t equal to 0, y is 0. So the potential energy comes out to be 0. We just have the kinetic energy, and this is 0 plus half m omega square times a square minus 0. So you get it as half m omega square a square at t0. If we talk of, say, at the particle t by 4, at that time the displacement is equal to the amplitude. So we have at t by 4, that means 1/4 of the complete cycle, your energy would be u plus k again, but this time it would be half m omega square. In place of y, I would put it as a, because at t equal to t by 4, my y is equal to the complete displacement, maximum displacement amplitude. So this will be a square, and this bracket will become a square minus a square is 0. So again it is half m omega square a square. So like this we can check it out at various different specific time intervals, and we get that the total energy of a simple harmonic motion is constant at all times, and that is equal to half m omega square a square. I hope you understood how to calculate the total energy in simple harmonic motion. If you liked the video, please follow us, subscribe us on Instagram and Facebook, and do subscribe us at YouTube. Thank you for watching.